Hello, Algebra 2. Tonight's topic, Day 3 notes. You can add Day 3 here onto your notes, and there are 3 learning targets. Now, I know the first 2 you'll have a good understanding after tonight's notes, but I do know number 3 learning target we'll have to spend lots of time in class over the next couple classes making sure you understand number 3. So the first learning target is I can recognize the parent function in vertex form of the quadratic function. The second one is I can graph and write the equation of quadratic functions and inequalities using a transformational approach. And the third is the one where we're talking about all the properties of the graph. And the target is I can find the x and y intercepts, the domain and range of a graph. This you might already be able to do based on Unit 1 and Algebra 1. The next part I can also determine the increasing and decreasing intervals and end behavior of the graph. Increasing and decreasing, we've already talked about how a graph does that from left to right. We look and determine if it's increasing or decreasing. Now we're going to be listing them in the intervals. And end behavior of the graph is going to be a new vocabulary word for this unit. Last, I can find the relative maximum and minimum points and the axis of symmetry of a quadratic graph. Okay, let me fix the spelling there. Okay, that looks better, and I've added Day 3 to help organize your notes. All right, so first we're going to introduce the quadratic function with a real-life scenario. And when we're thinking about the sport soccer, you see the ball go up in the air sometimes, and sometimes it stays on the ground. But in this example, we're talking about a ball that's been headed by a player who's 5 foot tall. So it's in the air. And usually when I introduce this in class, I talk about what position someone might be playing if this happens. So as you know, if you've seen a soccer game, the defense would probably have the ball go up higher in the air to get it out of the penalty box, and where the offense would be having it not have much of a air, they're trying to shoot it right into the goal with their head. So this example is more like a defender or a midfield heading the ball and it goes up higher in the air. And we have a table that they say the soccer player is 5 feet tall, and it lists a table to tell us what happens at each second. So I want you to go ahead and pause the video and graph this table onto our coordinate plane. Our time will be our x, our independent variable, and our height will be our y. So you're going to graph it on here, and you can spread out your intervals more, or you can use the grid that you have here. So go ahead and pause the video and see what you get when you graph that table. Okay, so when you plotted your points, you should have 0, 5, and I decided the height that I would go up by 1 unit. Each grid would say 1 unit, be 1 unit. But in my time, I decided to go by so this would be at 1/2 second, and this would be 1 second, just to kind of give a better picture of my shape here. So they weren't all smushed together here. So I went by a 1/2 second was equal to 1 grid. So at 1 second, our height was at 10. And then at 2 seconds, our height was at 13. And at 3 seconds, our height is 14. And then so on and so on. So you should have a symmetric looking graph where you can see the ball at these points at each part. And I want you to go ahead and connect your points here. Okay. And then this shape is a parabola. You probably remember that from Algebra 1. This shape has a parabola shape. It's a quadratic, and one application, one place we see parabolas is in sports. And in this case, our soccer ball, it started off on being headed by the 5-foot tall player who heads it out of the penalty box and then goes all the way up 14 feet and then comes back at 5 feet. Now we don't have any more data, so we don't know if someone else headed the ball at that point or if it was controlled and brought down and then passed on the ground. But that's all the data we have, so we're going to stop there and then think about our questions. So go ahead and try to think about these 3 questions, and then so pause the video and answer those questions and bring it back. Okay, so the ground, you should have determined that the ground here is at 0 feet. Anytime you think of the ground, it has no height. So the ground is at 0 feet. So right here is the ground, any point here. The highest point the ball will reach, this is our maximum point. That, if you look at the data, it shows that at 14 feet, at 3 seconds, the highest the ball is 14 feet. And the last question, is the path of the ball symmetric? And that's yes. We could put a line right down the middle, and we call this the axis of symmetry. And if you remember from the absolute value unit, that it also had an axis of symmetry. So this line would down the center would cut our graph in half, and if we folded it, say we had a piece of paper with this on it and we fold it in half, it would fold this point over to here, this point to here, and this point to here. And that's what it means by symmetric. We could fold it in half and have the same parts. So yes. Okay. I want you to go ahead and label a few things. The first, let's label what we just talked about, the axis of symmetry. Now remember, this is an equation, and it's a vertical line. So remember, our vertical lines equations are x-equal equations, and where they go through the x-intercept is the equation. So remember, each point on this line has the same x value. So the equation would be x equals 3. Also, let's label the maximum point. This parabola has a maximum. We talked about it was at the 14 feet. And that would be our maximum point. And our maximum is also the vertex when it comes to the parabola. Just like in our absolute value graph, our vertex and either the minimum or the maximum, they're going to be the same. So in this case, our vertex is this maximum point, and the coordinates would be, the x value would be 3 and the y value would be 14. So it would be at 3, 14. I'm going to change colors just to make sure you realize. So the vertex is this point, and it's also called a maximum. Okay. Our x-intercepts, in this case, we don't know if it hits the ground yet. So we only have this much data. So at some point, unless they juggle for a really long time, at some point they will stop juggling and it will hit the ground. So at some point it will, but all the data we have, we don't know when that is. So we don't have any x-intercepts. So I'm just going to write none because the data stops. But if we had a point that went through here, it would be the x-intercept. And remember, x-intercepts are also called zeros. Okay, a few things before we stop. And the first one is the parent quadratic function. So our parent quadratic function is y equals x squared. So remember, we have the other parent functions of a linear parent function and an absolute parent function. So go ahead and pause the video and see if you remember the equations of the parent linear function and the parent absolute value. Okay, the parent linear function, remember, was y equals x. It was a line with a slope of 1 through the origin. And the parent absolute value function, remember, is y equals the absolute value of x. And remember, the vertex was at the origin and the a was equal to 1. So it had this shape. Our parent quadratic function is y equals x squared. And our a again will be 1 and our h and k are 0. So first, let's go ahead and plot some points in to see what this graph looks like. Remember, we would just try some values to see what it would look like. Go ahead and substitute try these 5 values to see if you can get a good picture of what this graph looks like. Substitute them in for x and come up with a y. Go ahead and pause the video and try that. Okay, so remember, you take each x value and you substitute in for x. Always use parentheses when you do that, especially if you're using your calculator. So when you have the -2 squared, remember, that means -2 times -2, and that would be +4. Then when we substitute in -1, we would substitute that in for x, and we would have -1 squared. So -1 squared would be equal to 1. And then 0 squared, we substitute in 0 in here for x, and 0 squared is 0. We substitute 1 in for x, so 1 squared is 1. And then we substitute 2 in for x to get our y, and 2 squared is 4. Okay, go ahead and plot these points on our coordinate plane, and then bring it back. Okay, your picture should look something like this, and you should have connected your dots and drawn 2 arrows, because you know both sides would continue to go up. If we were to substitute in 3 here for x and -3 for x, we would get either way, 3 squared and -3 squared would be 9. So you know the function will continue to go up no matter what. The other thing you need to draw is your axis of symmetry. Remember, it's a line that cuts your function in half, and it will be symmetric. So it goes through the vertex here, and our vertex in this case would be a minimum point. All right, the last part for the notes today, and then we'll work on the rest of this in class, is understanding our vertex form. So we'll have the same a, h, and k that we've been working with the absolute value. So this is the equation, y equals a times x minus h squared plus k. So remember, a is our value that changes the shape, h moves it left and right, and then k moves it up and down. We're going to talk more about this in class, Just understand that our transformations from the parent graph in this case, remember, is y equals x squared. We'll see you in class.